In 1924, the son of President Calvin Coolidge developed a small blister on his foot. Within a week, he died from a bacterial infection. Now, because we have antibiotics today, you probably won't die from a blister on your foot or a paper cut on your hand. But we are slowly approaching a reality reminiscent of the pre-antibiotic era because bacteria are becoming resistant to antibiotics, meaning that antibiotics are losing their effectiveness. By 2050, it is predicted that 10 million people will die every year from antibiotic-resistant bacteria. So, if antibiotics are failing, what else can we use? Well, it turns out that bacteria have natural viral predators called phages. There are more phages on Earth than there are stars in our galaxy. And because phages only eat bacteria and not our human cells, this makes them powerful allies. But here's the catch. Not only can bacteria evolve resistance to antibiotics, they can also evolve defense mechanisms against phages. So think of bacteria as fighters, wielding both swords and shields. The swords allow them to fight antibiotics, and shields protect them from phages. Fortunately for us, bacteria often cannot wield both swords and shields together, but we still don't understand how bacteria make these trade-offs. This is where my research comes in. I use machine learning, a subset of artificial intelligence, to map out these sword and shield decisions at scale. Basically, I train a computer to recognize patterns across thousands of experimental data that we humans cannot easily see. I give the computer two things: the genetic information inside bacteria, such as the genes that encode the swords or shields, and the bacterial response to antibiotics or phages. This allows the computer to learn and predict which genes tip the balance scale towards the shield and which tip it towards the sword. From this work, we can see that some shields make bacteria more vulnerable to specific antibiotics, and vice versa, some swords make it easier for phages to attack. With these insights, we can exploit these weaknesses and design smarter treatments using both antibiotics and phages to trap bacteria in a lose-lose situation, so that we can outsmart them before they outsmart us. If we fail to resolve the antibiotic resistance crisis, we edge closer to a world where small wounds will kill again, and where 10 million lives are at stake every year. My hope, and the reason why I do this research, is so that no one's life hinges on something as small as a blister again. Thank you.